Hi, I'm Rachel.
And I'm Brian.
And I know you feel the pull to watch this video because in this episode of Mythbusters, we are going to prove to you that the bigger the magnet doesn't always mean it is stronger.
Rachel, do you know what magnets are made out of?
Actually, I'm not sure what magnets are made out of.
All magnets are made of a group of metals called ferromagnetic metals. These are metals such as nickel or iron. Inside a metal, like iron, there are lots of tiny little magnets that all start off pointing in different directions. To make it a magnet, you need to make all the tiny magnets line up. To do this, you heat up all the material and put it in a magnetic field. Then, when the material cools down in the magnetic field, they'll all be lined up and you'll have a magnet. For a very strong magnet, you need something that will make the tiny magnets in the metal stay in the right position right after it is cooled.
Wow, that's really cool. I didn't know that. Brian, do you know how a magnet works?
I do not.
Okay, how a magnet works. A magnet is an object that has a magnetic field. It attracts various objects, like pieces of iron, nickel, cobalt, steel, things like that. In the early days, the Greeks observed that the naturally occurring Ido stone attracts iron pieces. From this observation, and that day onward, they began the journey to the discovery of magnets. These days, magnets are made artificially in various shapes and sizes, depending on their use. One of the most common magnets is the bar magnet. It's like the long rectangular bar that is uniform cross-section that attracts pieces of various objects. The magnetic compass needle is also a commonly used type of magnet. The compass needle is a tiny magnet that is used to freely move horizontally on a pivot. One end of the compass needle points to the north direction and the other end points to the south. The end of a freely pivoted magnet will always point to the north-south direction. The end that points to the north is called the north pole of the magnet, and the end that points to the south is called the south pole of the magnet. It has been proven by experiments like magnetic poles repel each other, whereas unlike poles will attract to each other.
Wow. Do you know what a magnetic field is?
I kind of do, but I'm really not that sure.
Well, the space surrounding a magnet in which magnetic force is exerted is called a magnetic force. If a bar magnet is placed in such a field, it will experience magnetic forces. However, the field will continue to exist even if the magnet is moved. The direction of the magnetic field at a point is the direction of the resultant force acting on a hypothetical north pole placed at that point.
Oh, that makes sense. Do you know how a magnetic field is created?
Not sure.
Well, when a current flows in a wire, a magnetic field is created around that wire. From this, it has been inferred that magnetic fields are produced by the motion of electrical charges. So a magnetic field of a bar magnet thus results from the motion of a negatively charged electrons in the magnet.
Now we're going to talk about magnetic lines of force. Just as an electric field is described by drawing the electric lines of force, in the same way, a magnetic field is described by drawing the magnetic lines of force. When a small north magnetic pole is placed in the magnetic field created by a magnet, it will experience a force, and if the north pole is free, it will move under the influence of magnetic field. The path traced by a north magnetic pole free to move under the influence of a magnetic field is called a magnetic line of force. In other words, the magnetic lines of force are the lines drawn in a magnetic field along with north magnetic pole it would move. The direction of a magnetic line of force at any point gives the direction of the magnetic force on a north pole placed at that point. Since the direction of a magnetic line of force is the direction of a force on the north pole, so the magnetic lines of the force always begin on the north pole of a magnet and end on the south pole of the magnet. A small magnetic compass, when moved along a line of force, always sets itself along the line tangential to it. So a line drawn from the south pole of the compass to its north pole indicates the direction of the magnetic field.
Did you also know that there are several properties to the magnetic lines of force?
I know.
The first one is the magnetic line of force originated from the north pole of a magnet and ends at the south pole. The second one is the magnetic lines of force come closer to one another near the poles of a magnet, but they are widely separated at other places. The third is the magnetic lines of force do not intersect or cross one another. Fourth is when a magnetic compass is placed at different points on a magnetic line of force, it aligns itself along the tangent to the line force of that point. These are just some of the basic concepts of magnetism. One cannot possibly grasp the depth and appreciate the versatility of magnets without reading more about the use of magnets. The Earth itself is a huge magnet, and electromagnetism among other things.
Now we're going to prove to you that a bigger magnet isn't always the strongest magnet. For our experiment, we're going to take a big magnet and a small magnet and see which one can hold more washers. This is the big magnet. And for the big magnet, it can hold 1, 2, 3, 4, 5, 6, 7, and only 7.
Okay, for our smaller magnet, it can hold 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and on the 17th one it has trouble. So, as you can see, the bigger magnet was only able to hold 6, while the smaller magnet was able to hold 16. So, as you can see, sometimes strong things come in small packages.